Okay, so here's kind of what we've looked at so far, right? We talked about homolytic versus heterolytic. We talked about stabilities of radicals, and we talked about the radical halogenation of alkanes, and we also went through the steps in the reaction, right? The chain reaction. So, allylic radicals, what makes them special? Okay, well, I didn't say they were special before, but they are special. Okay, so let's just imagine to form an allylic radical, we need to remove an allylic hydrogen atom. Okay, so I'm not going to worry about the actual mechanism here first. We're going to remove a hydrogen radical, and we would then get an allylic radical. Okay? So this allylic radical, just like an allylic cation or an allylic anion, can be stabilized by resonance. Okay? And the way that we draw this for allylic is that we're going to use these single-sided arrows. So that one is going to combine with one from the pi bond, and we're going to split that pi bond like this. And we get another resonance contributor like this. Okay, so remember, when we have resonance, these two structures don't equilibrate, they don't go back and forth, but what actually is the real structure is that radical is just spread equally over those two terminal positions, right? We have partial double bonds between both sets of carbons. So because we have this stabilization, so this is stabilized by resonance, that makes these allylic radicals more stable even than the tertiary radical. And in fact, if we substituted this allylic radical and put more substituents on the ends, that would make it even more stable, right? Because we're combining both the allylic nature and the substitution. Okay? Another type of radical that's similar to this, and I'm going to kind of include it in this, is radicals that are generated at this position here. Do you know what the position next to a benzene ring is called? This is the benzylic position, right? And benzylic radicals are also stabilized by resonance, right? I'm not going to draw all of these, but this could move in this way. It could combine with one of these pi bonds, and this pi bond would split, excuse me, to form a radical like this. Okay? Yeah, question?
Is this how antioxidants work? Where they move the radical throughout?
I think they can, antioxidants. Well, a lot of times what they'll do, there will be these activated oxygen species, which are oftentimes radicals, and they can intercept those radical oxygen species. Yeah. Okay, so, and then this is going to work. This radical can delocalize again to here, right? And then again to here. So we're spreading this radical all the way around this benzene ring. Okay, so that helps stabilize this. And the reaction that we're going to show, we're just going to talk about it. I'm going to show you how to do it for allylic positions, but will work for benzylic positions as well. Okay? All right, so let's look at the reaction. We've got a new reagent here. Okay, this is called N-bromosuccinimide. But we can just remember NBS. okay? And this NBS is going to essentially be a way to generate bromine radicals, okay? And when we do this reaction, we'll just draw out the product first. We are going to do a substitution, and we're going to generate the allylic bromide. Okay, so it's not adding to the double bond, it's adding to the adjacent, or substituting at the adjacent allylic position. Like I mentioned, we could also do this same reaction on the benzylic position. So if we just wrote in NBS and H nu, or heat, I think works as well, then the reaction will not happen in the benzene ring, but will happen at the benzylic position. Okay? All right, so let's see how it fits into the different reaction stages that we talked about yesterday. All right, so we're going to use a slightly different substrate here. We just have this but1ene, and so we can get the allylic substitution at this allylic position. However, we get another product out of this reaction as well. And this product looks like this. Oops, that's an R. Okay, so how would we get these two products? Yeah.
Resonance?
Yeah, it's because of the allylic resonance. Okay, so let's run this thing through. So we're going to start out here with the NBS. Okay, and that's what's going to be involved in the initiation. Okay, so we have NBS. We shine the light on this, and we get a homolytic bond cleavage of that nitrogen-bromine bond. Like this. And so that gives us this radical plus the bromine radical. And it's the bromine radical that we would like. Okay, eventually along the way, this NBS byproduct is going to pick up a hydrogen. So instead of N-bromosuccinimide, it's going to make succinimide.
Question?
Yeah.
For the test, when we were writing a synthesis reaction, would you like us to put initiation, propagation, termination?
Yeah, so two comments there. This is not what I would call a synthesis problem, right? This is a reaction mechanism problem. So if we do synthesis, you only have to draw reactants and products and reagents. You don't have to draw out all the arrows. In a mechanism one, yes, I will. If it's a radical mechanism like this, I will want you to label out the stages, okay? And that's what I'll ask you to do. So initiation here, we've generated this bromine radical, and that's what we need for the reaction. Okay, so in the second step is the propagation. Okay, and so this involves, just like before, the reaction of our actual organic substrate with the bromine radical. And this is going to abstract one of these hydrogen atoms. Okay, because we have to generate that allylic radical. Like this, plus HBr. Okay, of course this has two resonance forms. And both of these can participate in the next step.
Question.
Yes?
Would it be appropriate just to, instead of drawing out whole products, just draw like a structure with resonance with dashed lines? Or maybe
I think, so the question is, so we know that the kind of true hybrid structure we can draw with kind of a, I guess here, usually it's a delta plus or minus, we could kind of have a delta dot, I guess, and then dashed lines here and here. I think for the actual mechanism, I'd rather see the different contributors, okay? All right, so the next step in the propagation then is going to be the reaction of the allylic radical with something that we can't really see in the reaction step here, but it's going to be reacting with bromine, okay? And bromine in this reaction, the reason that this works is because there's just always a little bit of bromine as more or less a contaminant in NBS, okay? We don't really show that, so this comes from the NBS. And it helps us that there's only a small amount here because that minimizes a competing reaction that we could have, which would be what? If we have bromine in this reaction. Right, bromination of the alkene. Okay, so it minimizes that reaction because we have a small amount of bromine. The other reason I think we don't get bromination very much is because those cations, like the bromonium ion with a full cation, is a higher energy than these radicals. Okay, the radicals, remember I said there was less energy difference between the different radical species. Yeah.
With our propagation step, is the terminal or the internal alkene the more favored resonance?
Okay, so the question there is if we have these two resonance here, so it would be in this next step, right? Is it going to be favored to brominate, well, even at the top, do we get the left product or the right product, right? So I think we're not going to really try to predict that so much. We're just going to say we can get the mixture of either, or of both. What we will say is if we have an allylic, an alkene, we're going to remove the hydrogen. If we have two allylic positions, we're going to remove the hydrogen atom to form the most stable allylic radical, okay, which would be the more highly substituted one. Okay, so we go to here. Oops. Just like when we were doing the bromination then, this radical reacts with bromine. And this is going to form one of the products, like this, plus Br radical. Okay, just because I don't have much room here, I'm going to say that for our mechanism, what we're trying to do is just form this one. And that's probably how I would do if I asked you for an actual mechanism. Like I said yesterday, I'd say, how does this molecule go to this? Okay, we could do the same thing to get to there. We would just use another reaction of this terminal primary radical, okay? Okay, so what's the last step here? The termination. Okay, and so we have a number of different things, and what I'm going to do, for example, if this type of problem would show up on an exam, that I'll say, show me at least maybe 2 possible termination steps. Okay? Because we have that NBS, this radical up here, we got bromine, we could have even more, and so there could be, you know, a bunch of different termination steps. And so you don't have to spend too much time writing out 6 termination steps. I'm just going to say probably to ask you for a couple of those. Okay? So for our example, we could say have another bromine and a bromine go to Br2. right? We could have two allylic structures. Let's just do this really, let's do it in a really fun way. We'll combine the secondary position of the allylic radical with the primary end. So then if I can do this without getting too confused, I'm getting too fancy here. There's the end and here. So it forms something like this, right? Or we could, you know, combine a bromine radical with one of these other ones. And so these are just a couple of the possible ways. Remember, termination is going to be the process of taking any two radicals that are generated in the reaction and combining those to consume radicals to form non-radicals. Okay? Yeah, question?
So you said that we avoid using elemental bromine so that we don't have nucleophilic, nucleophilic elimination. Do we have any options to do allylic chlorination that will avoid?
I think, so the question was, could we do allylic chlorination as well? And I think you can with just a chlorine analog of MBS. Yeah. Yeah, question?
You said that you'll tell us how many terminations you exist. Are you do the same thing for propagation?
No. So propagation, I always want to see all the propagation because that's the chain reaction. That's the most important part of the whole reaction mechanism. Because if we leave one of those out, we can't really see how it's happening. Yep. Question up here. Not really, though. If we have we probably have a small amount of that. And it's probably, it can pull up, it's probably going to say pull off a hydrogen off of HBr or the hydrogen off of here. And I think it usually shows up as just having a hydrogen on there. But it could combine with one of the other radicals. But because we're only using a small concentration, it wouldn't be a very big part of the product mixture. Okay? Anything else? Yeah, in back there.
So would the formation of additional product be considered a termination step as well, with the additional bromine?
Well, so the question is, would the formation of additional product, so if you were forming, we do have termination steps that do form product, right? So if either of these two resonance contributors, or if this allylic carbocation combines with bromine radical, then you do form product. Okay, but that's a small contribution to the product formation. Okay, so if you're drawing out a mechanism, then I don't want you just to generate this and then combine radicals as a termination and say that's how the product formed. Okay, that's why we need to show the whole propagation cycle. Okay? Yeah?
Do we need to show arrows on termination?
Yeah, well, if I ask you to show arrows, then you should show them all. Yeah, so let's show them. Just for fun. Those two, those two. All right? All right. Okay, so let's just look at a couple of examples then. Okay, so when we draw out products, we need to make sure we take into account the possible resonance of that allylic radical. So we always know that we can brominate at the allylic position of the structure that's shown, right? And either side would be the same here, but we're always going to get a second product. All right, so where would this alternative position be for the other product? Okay, so it's going to be up here on the position there, and the double bond's going to be shifted down like this. All right. We do the same thing for this. We can show our first bromine down here hitting this allylic position, right? Okay, draw out the other one before I do it. Okay, it's always going to have the same carbon skeleton here. We're always going to shift the doubled bond down to the position where the first bromine is, and we're going to put this bromine up over here. All right? You had a question or no? Just needed more time? Okay, so we've got one more reaction to take a look at.
Can you go back to the previous slide for a bit?
Okay, I'm going forward now. Just trying to slow me down, aren't you? Okay, so we all know just the electrophilic addition of HBr to an alkene, right? The alkene gets protonated, forms a carbocation, always forms the most stable carbocation. So the carbocation is at the more substituted end, right? And then bromide comes in and reacts with that carbocation. So we get a bromine at the more substituted side, right? It's following Markovnikov's rule. If we make one small change to this reaction and we add some peroxide to the reaction, so peroxide is something that has an oxygen-oxygen bond. If those R groups are hydrogens, then this is hydrogen peroxide. And we're just going to put R's. We don't really care what those are at this point. If we add peroxide, then the reaction changes to put the bromine on the terminal end. Okay, so we could call this an anti-Markovnikov addition. Right, this one up here followed Markovnikov's rule. Okay, so now we have an alkene, an unsymmetrically substituted alkene. We have the possibility of putting the bromine on either position. Okay, that's pretty exciting, right? We have a lot of flexibility there now. So we've made a change in the regioselectivity of the reaction. Okay, so what on a kind of fundamental point of view, what does that suggest to us about the mechanism? Can it have the same mechanism as the reaction up on the top? No, because we have a complete flip in regioselectivity. It suggests that the mechanism has changed as well, right? So something big has changed. All right, we could do this reaction again. Here's just another example. If we have this alkene here, we can put the bromine out on the terminal position. Okay, so we've added, right, an H here and a bromine there. Okay? All right, so what kind of mechanism do you think this involves? Oh, a radical mechanism, right?
For the second reaction, how did I know that the peroxide was going to add to the side of the chain?
Oh, that hasn't added there.
Okay.
You wouldn't know that because it doesn't happen. All right, so let's take a look at how this one happens.
Dr. Davis,
Yeah.
any question on the last slide?
All right, so let's take a look at how this reaction proceeds, okay? So what do you think we're adding the peroxide for? What's it going to do? It's going to be the radical initiator, okay? So we always start out again with our initiation. So in this case, if we take a radical and we heat that up, the oxygen-oxygen bond is pretty unstable. It's not very strong. And so we just get a homolytic bond cleavage of that oxygen-oxygen bond. And so we get 2 oxygen radicals. Okay? But the initiation really doesn't stop here. We have to have another initiation step because the initiation isn't going to be finished until we create a radical that's involved in the chain reaction of propagation. Okay? And so what's going to happen is that this oxygen radical reacts with HBr, pulls off this hydrogen atom, and forms an alcohol plus the bromine radical. Okay, and it's the bromine radical that we need for the propagation steps. Okay, so took these 2 steps of initiation to get there. Okay, now we can do propagation. Okay, so again, like in every case we've seen, the propagation is the first step that really involves our organic substrate up there. Okay, so in this case it's going to be the alkene reacting with the bromine radical. Okay, and this time it's going to be the pi bond that reacts with the radical. So this is going to react over here with that. And it's going to react in such a way, let's draw both possibilities, to form the more stable radical. Okay, so if we're going to form the more stable radical, do you think that that radical is going to end up on this position here, which would be secondary, or the position out here that would be primary? The secondary one, right? That's more stable. So where does the bromine have to go then? It has to go on the end, right? So the bromine could go here to form a radical there. Or the other alternative is that it would go here to form the radical out here, right? But we know that this one here is more stable. And so this one's not going to form very much at all, okay? All right, so have we made the product yet? No, so we have to have another propagation step, right? So we're going to take that radical with the bromine on it. And this is going to react with HBr. Okay, and it's just going to pull off the hydrogen.
Question.
Yeah.
Do we, like on an exam, do we need to draw both products or just the more stable products?
So the question is, would you need to draw both of these? I think, like I kind of mentioned before, on a mechanism problem, what I would do is something like up there, because I'd say, oh, how do we generate this product, right? And so I really don't need, this isn't really constructive to get to there, but I'm just trying to explain the selectivity. Okay, good question. Okay, so now we're going to put our new hydrogen here, plus we formed bromine radical. And just like before, this bromine radical can then go back up and react with another alkene. So this is our chain reaction. Okay? Now the termination for this one, and I never leave myself much room down here, has a lot of different possibilities, right? Because we have the oxygen radicals, we have the bromine radical, we have the carbon radical, So we have quite a few possibilities. So let's just draw, we got bromine radicals, so let's just draw a few of them in here. So we could start with something like this radical plus could react with a bromine radical. Like this. That would form a dibromo compound. That'd be like we were just brominating the alkene, right? We could again have bromine radical plus bromine radical gives us Br2, right? We could, what else could we do? We could have two of these radicals combined together, right, to dimerize that piece. We could have an oxygen radical combined with this radical to make an ether, right? So there's a bunch of different choices. All right? Yeah, question?
For that first propagation, do we need to show where that other electron goes in the pi bond?
Oh, yes, we should. Thank you. So this should show over to like that. Yep, good. Thank you. All right? Yeah, question? I think, so the question was how much peroxide do we need? But I think like with the other examples, we want to keep the concentration of radicals reasonably low, or else we get too much of the termination process going on. And so I think it would still be a reasonably small amount. I don't know an exact amount to give you, but it would be a low amount. Yeah, question?
Would there be any termination steps for the non-stable product formed in the first propagation step?
Oh, for here?
Yeah.
Well, if any of this forms, it could be a termination step. But we saw with bromination before, it was very selective. This is a little different. I'm not quite sure what the ratio there is. If
this were an exam question, you wouldn't want us to show that.
Yeah, I think for an exam question, since we're not really focusing on this one, and I only put it in as a matter of discussion, we probably wouldn't use it.
Okay.
Just make sure that those termination steps just involve two radicals from the mechanism coming together to form a non-radical. All right? Yeah, so that's a good question, and it's it's how much of these byproducts would we get? And I think that's again the reason why we want to make sure that the amount of peroxide that leads off to the formation of radicals, it all stays at a low concentration. Because if we don't have very much peroxide in the beginning, then we don't have very many radicals, and so when it terminates, we won't have very many termination byproducts. Let's quiet down, please. Yeah, one more question.
What's to stop just HBr from adding to the alkene?
Yeah, so that's a good question too. So, we clearly have a competing reaction of HBr just doing an electrophilic addition reaction. So I think a part of it is that when we form the radical, the pathway to form the radical is a lower energy process than forming the carbocation. So I think as long as we form the radicals right away, if we mix the alkene with HBr and leave it for a while before we shine the light on it, then we run the risk of having a lot of just electrophilic addition reaction. So, so we probably have, I've never run one of these reactions myself, so the practicality of the stepwise procedure, whether if you can, irradiate the peroxide first without and then you could have the alkene and the peroxide together, right? Shine light on that to generate some radicals and then add HBr to it. Maybe it's something like that to minimize that problem. Okay, so one other issue is if we're going to do either this bromination reaction or the addition of HBr and peroxide, and we are generating, either we have a chiral center or a stereogenic center, or we're generating one, what happens to the stereochemistry? Okay? So let's think about this reaction. If we're going to brominate this molecule, where is the bromine going to end up in that structure? Right, at that tertiary position. Okay? So what we have to think about to understand the stereochemical outcome is what's the intermediate going to look like, you know, at that position. So we know that along the way here, we're going to end up forming a radical at that position. And I'm going to draw it kind of on the side like this. And remember, the radical is sp2 hybridized, and that single electron is in the p orbital of that sp2 hybridized carbon. Right? In the last step here, remember it's bromine reacting with the radical, and because this is planar, it can react either on the top or on the bottom. Okay? There's not a difference between one side or the other. So if we form a radical, we should get a mixture of products. So the bromine could be on the back, or the bromine could be on the top. If we only have a single stereogenic center, then we should get a 1-to-1 mixture of these. So what's a 1-to-1 mixture of enantiomers? A racemic mixture. Okay? Same thing is really true for this addition of HBr here, but in this case, really that's not where the bromine is going, right? If we want to draw the important intermediate here, we would have, let's say we have the radical here, and we added our bromine onto the end, right? Because the bromine adds first, the bromine radical, to form the more substituted carbon radical. And so in the last step, how does that end up with a hydrogen there? What does it react with? With HBr, right? Right? And so again, in this case, it's the H here that's coming from the top or the bottom, which gives us, let's see how to draw these, a new chiral center, not where the bromine is, but where that methyl group now is. So we could get that product plus this product. Okay, and again, because we have a single stereogenic center here, we would expect to get a racemic mixture. Okay, so even though, like on the top one, we could start with an enantiomerically pure material, just one enantiomer, but if we ran this reaction, we'd end up with a racemic mixture. So we kind of lose all stereochemistry at that center. Okay? That make sense? Couple of minutes we have left here, and I'll fill in. I got a couple more examples, and I'll fill them in when I get back to my office if we don't do them all right now, and you can look back at the examples. So here's just a few examples. And so in this case, we're starting with this propylbenzene, and we want to get this diol. All right, so we can do like we did before, right? We can move forward from the reactant. So especially since we're in this chapter, how are we going to put a bromine on to that molecule? That's the only thing we know how to do in this chapter, right, is add a halogen. So we want to add, where do we want to add a bromine? Right, to a secondary position, but which one? There's a unique secondary position. The benzylic position, right? So we can use that reaction with the NBS and H nu. And so that's going to put a bromine at the benzylic position. Okay, let's go work backwards from here. How are we going to end up with a diol like that? Notice the diol, the stereochemistry, right, is anti. Yeah, so maybe we could make this from an epoxide. Like this. And we can open that epoxide either with hydroxide, or we could use acidic conditions as well. Okay, what do we make the epoxide from? An alkene. And we're going to want that transalkene. Okay, how do we do that? We can use the peroxy acid. CO3H. And then this involves an elimination reaction, right? So we just need a strong base to do that. It's an E2 elimination. All right? Yeah?
Using that methoxide for the base, wouldn't that also give a substitution because it's secondary?
So the question is, because it's secondary, could you get some substitution? Yeah, we could maybe use a little bit bulkier one. Might, even enhance the elimination versus substitution. Yeah, so there's two more examples here, this and the next page, and I'll fill those in with some things so you can look back at those if you want. So remember, there's the other review session tonight. And and the thing that I keep forgetting that I need to do is I will be posting on Canvas the room assignments for the exam. Okay, so I will see some of you that are assigned to my room on Monday.
Can you answer a question for me?
Yep.
Okay.
Oh, here. All right, let's finish today's notes. Okay, we've got another synthesis example here. So like the one above, we can start in the forward direction from our reactant, and we can work backwards from our product. So we're doing radical chemistry here, so the first step, obviously, is going to be the radical bromination. We want to brominate rather than chlorinate because bromination is so much more selective. This is going to put a bromine at that tertiary position. If we work backwards from our product retrosynthetically, we see that we've added an H and an OH, so we've done a hydration reaction. But it was done in the anti-Markovnikov direction. So we're going to make this from an alkene, and then we need to make that alkene from the bromide. So we need to just add our strong base. This is a tertiary alkyl halide. It can't do substitution, so this would be an E2 elimination. What about this reaction? How do we do this anti-Markovnikov hydration? This is a hydroboration oxidation reaction. Oh, that's wrong. That's the second step. pH3, and in the second step we use hydrogen peroxide and base. Alright? Example. Okay, so same strategy, right? So we are going to move forward here. Again, as we're starting with an alkane, we really only have one good reaction. Bromination at the tertiary position. If we move backwards from here, okay, what can we make a ketone from? Well, we can make a ketone from an alkyne, but we don't really have the alkyne here. The other thing we could make it from is an alcohol, right? And we could convert that alcohol to the ketone by an oxidation reaction. So we would either use chromium trioxide or chromic acid, or we could use pyridinium chlorochromate, PCC. Alright, so we could make this alcohol by a hydration reaction, but we're going to have to make it, since we need to, let's go this way now, let's do the elimination. So we do the elimination, follow Zaitsev's rule to give the most stable alkene, and so to get to that alcohol we need to do an anti-Markovnikov hydration. So this, again, like the last one, is going to involve borane and basic hydrogen peroxide. Alright, so these are just some examples on how we can convert alkanes into functionalized molecules.